Right, welcome to the online causal inference seminar. Today we're excited to have Zhimei Ren from the University of Chicago. We'll talk about sensitivity analysis of individual treatment effects, a robust conformal inference approach. We also have two people in Q&A today, Emmanuel Candes and our own Ying, who's helping also organize the seminar. After the talk, we're gonna have a discussion by Stefan Wager. The moderation today will be handled by Ying, so I'm quickly switching over to her now.
Yeah, so for today's questions, please submit in the Q&A panel just at the bottom of the Zoom window, and we will raise them to Zhimei when she stops for Q&A. And that's it. Then I think I should give the stage to Zhimei and get started.
Okay, so can everyone see my screen? Okay, thank you. Thanks a lot for the introduction, and thanks a lot for the invitation. So today I am going to present our work on sensitivity analysis of individual treatment effects, a robust conformal inference approach. This is joint work with Ying Jing and Emmanuel Candes, both from Stanford University. So our work is motivated by the question that gets to be asked in a lot of areas, whether this treatment is effective or not. For example, there is a new Alzheimer's drug, and we're of course interested in know whether this drug is effective in improving the patient's condition. Or in the COVID-19 case, we're interested in knowing whether this vaccine is effective in lowering the infection rate or lowering the rate of getting severe conditions. So to consider this problem, we work under the potential outcome framework. Suppose we have a sample from the population, and for each individual in this population, there are two potential outcomes. The outcome if the individual receives treatment, or the outcome, the individual without receiving the treatment. So of course, we cannot ever simultaneously observe these two potential outcomes simultaneously, because an individual is either treated or not. So often there is a treatment assignment mechanism that sends people to different groups, the treated group and the control group. In the treated group, we get to observe one of the potential outcomes, the potential outcome given treated, and in the control group, the other potential outcome. The thing is, we never get to observe both of the potential outcomes on one individual. So to be more mathematical, we consider such a model where we have IID samples from a superpopulation. And for each unit, for example, unit I, we get to observe, we have the covariate X, we have the potential outcome without being treated, Y0, and the potential outcome after being treated, Y1. And there is also a treatment assigned mechanism for this individual that follows from some distribution. And then together for each unit, it is represented by the 4-element vector xi, yi1, y0, and ti. So in reality, we don't get to observe the full vector because, as I said before, we can never simultaneously observe both of the potential outcomes. So what we get to observe is the partial observations. Under the standard assumption called SITVA, what we get to observe is the covariate xi, the treatment mechanism ti, and the outcome given the treatment status. For example, if you're treated, you observe Y1. If you're not treated, you observe Y0. So having a data set at hand, the next question would be, how should we evaluate the effect of a treatment? A natural first step is to consider the effect of the treatment in the whole population. For example, the average treatment effect, which is defined as the expectation between Y1 and Y0. So this is this roughly describes the effectiveness of a treatment in the whole population, but it is still a very coarse description of the effectiveness of this treatment. So what happens to a subgroup and what happens to some individuals? So one step further, we can take into the heterogeneity of the treatment effect and consider the conditional average treatment effect, which is called CATE. This is defined as the conditional expectation of y1 minus y0 given some characteristics x. But even if we are able to know this CATE, we still have not many sense how an individual would benefit from this treatment. For example, if we know exactly that this tau of x is 1, we don't know if for an individual, the treatment is like. The distribution of it can be like the image on the left-hand side, which has a light tail, or the image on the right-hand side, which has a heavy tail. They are very different. So in our work, we focus on the inference on individual treatment effect. We would call it ITE in the following. So as we know, this ITE, y1 minus y0, is a random variable. So it doesn't make too much sense to give a point estimate for this random variable. And also, giving a point estimate does not represent the variability of your estimation. So in a previous work by Li Hualei and Emmanuel Candice in 2020, they proposed that we should construct a predictive interval for the ITE that covers the true ITE for a desired probability. So this gives you uncertainty quantification and also gives you information on the individual treatment effect. And in their paper, they propose a method that actually constructs such a predictive interval that is valid without strong, well, almost in a model-free flavor. And it is the main assumption in their paper is that the strong ignorability condition holds, which states that the treatment assignment is independent of the potential outcomes given the covariates. So the main question in our work is that what happens if we further remove this strong ignorability condition? How should we reliably make inference on the ITE in this situation? So as an overview of our work, we consider a setting where there's a unmeasured confounding, and then we try to characterize the counterfactual distribution under this unmeasured confounding situation. And then we propose how to construct predictive interval for ITEs in this case that is valid if the observational data is confounded up to some extent. And then we make use of these predictive intervals to show how to make robust causal conclusions. And this is done by inverting a sequence of hypothesis testing. So all of these will be discussed in detail later. So so now the first step is to construct predictive interval for the ITE. There are different scenarios. In some scenarios, there's only one outcome missing. For example, for the treated unit, we already get to observe Y1. So the only thing that we need to do is to estimate or construct predictive interval for Y0. And there are other cases where both of the potential outcomes are missing. For example, there is a new patient coming, and then he or she does not receive any treatment assignment yet. So both Y1 and Y0 are missing. So for the first case, suppose we have a sample from the control group and we all have already observed the potential outcome Y0. The only thing that we need to do here is just to construct a predictive interval for Y1 and then take the difference to form a predictive interval for the ITE. In the latter case, where both outcomes are missing, what we do is to construct two predictive intervals, and then for Y1 and Y0 respectively, and then merge them to be a predictive interval for the ITE. So at the end of the day, the problem of constructing predictive interval for ITEs boils down to the problem of constructing a predictive interval for the counterfactual. So this is the main, so in the next step, we will mainly be talking about constructing predictive interval for the counterfactual. So before we dive into the construction of predictive interval, I am pausing for a while to see if there are any questions.
There is no online questions, so let's continue.
Okay, thank you. So I am going to, now we will start the construction. So let's first try to understand what's happening in the counterfactual prediction problem. As we said, the main difficulty in this problem is that we never get to observe the two potential outcomes simultaneously. For example, if we want to estimate Y1 in the superpopulation, we never know what is Y1 like in the control group. So for example, we just focus on predicting Y1 for the control group. So the training distribution is, of course, what we get to observe. So the distribution is the joint distribution of X and Y1 in the control group that is given T equals 1. And the target distribution is X and Y1 given T equals 0. So there's like, we can see from this formulation that there is a distributional shift from the training distribution to the target distribution. So let's let WXY denote the likelihood ratio between the training distribution and the target distribution. So in fact, recall that our goal is to construct a predictive interval. In a paper by Tibshani et al. In 2019, there is actually a general recipe for constructing predictive interval when there is a distributional shift. Although I say there is a general recipe, it is not always computable. It's computable in certain cases. So let me first introduce what this general recipe is like. So the framework is based on conformal inference proposed by Wolf et al. In 1999. So it starts like this. It first divides the observations into two sets, the training set and the calibration set. One can first train any predictive model on the training set. And then you can choose a residual function, Vxy, to evaluate how well this training model is. For example, you can take the absolute value between y and the predicted value of y. And then we would calculate the residuals on the calibration set. And the final prediction interval takes the form by thresholding this residual, where this cutoff here, V hat, is chosen based on the residuals computed on the calibration set. For example, one of the special case of conformal inference is CQR, conformalized quantile regression. So on the left-hand side, we have a training set, and on the right-hand side, we have a calibration set. And then this example, they have the same distribution. And then on the training set, we fit, for example, a quantile regression, and the two lines are the estimated low and high quantiles. And then we compute the residuals on the calibration set. Here, we define the residual to be the signed distance between the points and their estimate quantiles. And then we choose the threshold based on the residuals calculated on the calibration set. And then we cut off the residual and then invert it to be a predictive interval. So as I said, there's a general recipe for the case where there's a distributional shift. So actually conformal inference can handle both the case where there's no distributional shift or there is distributional shift. And the main difference is only in choosing the threshold V hat. So when the training distribution equals the target distribution, the threshold V hat is simply the 1 minus alpha quantile of the residuals calculated on the calibration set. And when there is a distributional shift, the threshold V hat becomes the weighted quantile of the residuals. So you can, because you know the weight here, PWI, actually depend on X and Y, where X and Y are the value you are to predict. So they're not always computable. A special case is that when wxy is wx, it does not depend on y, it's a covariate shift. We can compute this v hat so v hat becomes computable. So far we've introduced conformal inference, and we know that it handles any conditional distribution, any sample size, and any training procedure. And we also know that it can compute a valid predicted interval when the training distribution is the same as the target distribution, or there is only a covariate shift between the training distribution and the target distribution. So going back to our problem of counterfactual prediction, it is found by Li Hualei and Manicanos that in the setting where there's no confounding, that is the strong ignorability condition holds, there is only a covariate shift between the training distribution and the target distribution. So to be specific, recall that our training distribution and target distribution is like this. And then by Bayes' rule, we can expand the target distribution to be the marginal distribution of x and the distribution of y given x. And because the strong ignorability assumption holds, we can replace this t equals 0 by t equals 1. So now if we look at the ratio between the target distribution and the training distribution, we found that the likelihood ratio is actually only a function of x, and it is proportional to 1 minus e of x divided by e of x, where this e of x is the propensity score. So far, we know that the main problem in counterfactual inference is that there is a distributional shift. And we also have known that conformal inference is a tool to conduct predictive inference, and previous technique allows us to handle the case where the training distribution is the same as the target distribution, or there is only a covariate shift. And we also know that under strong ignorability, there is only a covariate shift between the training distribution and the target distribution. So current technique can handle this problem in a computable fashion. So next, we begin our research, which is what if the strong ignorability fails? The question is, the distributional shift is no longer a covariate shift, and the target distribution is no longer identifiable. So we do this by editing the conformal inference framework and add some robustness to it so that it can still be valid when there is unmeasured confounding. So here the setting is slightly different because we have an unmeasured confounder U that influence both the treatment and the potential outcomes. So let's say that now for each unit, we have a UI, which is the unmeasured confounder, and the same xi, y0, and y1. We also have the treatment assignment ti, which might depend on this UI as well. So as before, the observables are xi, ti, and yi, ti. Now the assumption, instead of the strong ignorability assumption, our assumption is that the treatment assignment is independent of the potential outcomes, conditional on both xi and ui. So this is not really an assumption because such confounders always exist. You can take this U to be the potential outcomes themselves, and this assumption just automatically hold. The next step is to model the strength of the marginal, the confounding strength, because we need to know like how the confounder is affecting both TI and the potential outcomes. So here we use the marginal sensitivity model called the marginal gamma selection condition to model the strength of the confounding. Basically, the marginal gamma selection condition requires the odds of being treated conditional on certain values of x and u to be only gamma factors away from the odds ratio of being treated conditional on only the x equals some value. So as you have noted that this marginal gamma selection condition is very similar to Rosenbaum's gamma selection condition. It is in fact a slightly weaker condition than Rosenbaum's gamma selection condition. So any validity result that hold under the marginal gamma selection condition also holds under the Rosenbaum's gamma selection condition. So now suppose we have a marginal sensitivity model, and suppose the true data generating process satisfy this marginal gamma selection condition. We can actually show, although the target distribution is not identifiable, it is partially identifiable in the sense that we can bound the likelihood ratio between the target distribution and the training distribution by functions of observables. So here actually we can, the right-hand side is the upper bound of the likelihood ratio, and the left-hand side is lower bound. We can see both of them are functions of X. In fact, this can be termed as a more general question, where the training distribution is P of XY and the target distribution is P tilde of XY. Although we don't know what the target distribution is, we do know that the likelihood ratio between the target distribution and the training distribution is upper and lower bounded by functions of X. And given this setting, our goal is to construct a predictive interval for yn+1 such that it covers the true target with 1 minus alpha probability. So if we can solve this problem, we can solve the counterfactual prediction problem. So before I introduce the procedure, I'm pausing for a while to see if there are any questions.
There have been a clarification question about the inferential target, which has been answered by Emmanuel, which is like, we don't need to stick to the control group. We can deal with other inferential targets, for example, an individual from the superpopulation. And there is a question from the audience asking, what are your favorite tools for building the conformal inference model, for example, bootstrap estimation or something?
Yeah, that's a good question. So based on my experience, my limited experience of working with predictive models, I find boosting methods to be, and also random forest methods to be most the best ones. But I guess it also depends on the settings, because I mean, for boosting method, they do not require too much tuning, and then they work universally well in the problems that I've seen so far. But yeah, I think it still depends a lot on the background knowledge. Yeah, thank you for that question.
Yeah, and another clarification question, which is about whether the strong ignorability condition is saying that whether the individuals are treated or not has nothing to do with the covariates, but it has been answered by Emmanuel in the chat box. Yeah, and for the audience, like for submitting the questions, please use the Q&A section for us to better track your questions and answers. Thanks. And I think we can continue.
Thanks. Thank you, Ying. Yeah, so now let me present how we actually solve the robust conformal inference problem. So here, as before, we first compute the residuals on the calibration data. And then, so recall that there are upper and lower bounds for the likelihood ratio, L and U. They might be known if you have background knowledge. If they're not known, we use the training set to estimate them, because they're observable, so we can always estimate them. And then we construct this predictive interval again by thresholding the residuals. Suppose, so remember in the general recipe, if we didn't exactly know the the distributional shift, we can just take the weighted quantile of the residuals. However, here we do not know the exact distributional shift. We instead take the supreme over all the quantiles for those distributional shift that is within the range. So this is a conservative estimate of what we should know if WXY is known. So it is obviously a valid one. The main question is, how should we compute this V hat? Can we represent it in a more clean way? So the answer is actually yes. So how should we calculate this threshold? So let V1, V2 to Vn be the order statistics of the residuals. So we can actually equivalently write the weighted conformal procedure as V hat equals Vk star, where K star is the smallest K, such that the ratio here is greater or equal than 1 minus alpha. But of course, this is an R quantity because we don't know what W is. So instead, the robust weighted conformal requires V hat to be this Vk hat star. This Vk hat star is the minimum K such that a slightly modified ratio is greater or equal than 1 minus alpha. So this modified ratio is nothing but replacing the original ratio by replacing every W by their conservative counterparts. For example, in the numerator, we are replacing W by this L hat, and then same for the denominator. So by doing so, this K hat star is a conservative estimate of K star. It is greater or equal than K star, so it is obviously a valid choice for the inference problem. We can also show that this choice of cutoff is optimal under the constraints on the unknown weights. So in our paper, we show that if the superpopulation satisfies the marginal gamma selection condition, then the predictive interval resulting from the robust conformal inference procedure is exactly valid when the upper bound and lower bound L and U are exactly known. And it is approximately valid when they are estimated, where the miscoverage rate depends on how well you estimate the upper and lower bounds, how aggressive these estimators are. So far, we've finished the first part of our work, where we considered the counterfactual inference under unmeasured confounding. We know how the distributional shift is like under the marginal sensitivity model, and there is a robust conformal inference method for constructing predictive interval that is valid in the finite sample case, and it is also model-free, robust to estimation error. But in our previous result, the guarantee is in a marginalized sense, meaning that the validity holds averaged over the realizations of the training and calibration data. So we may want to ask whether we can have some validity given the current data set. So this leads us to the next type of guarantee, which is the Pac-Type predictive inference. So here Pac refers to probably approximately correct. So the Pac-Type prediction interval means that we want a prediction interval such that it is valid conditional on the calibration set with probability at least 1 minus delta. So to do this, we again consider the prediction interval in the form of thresholding the residual. So here the probability of the new data set being covered conditional on the calibration data equals to the probability of the residuals being thresholded. And because this calibration data is independent of the new data point, this quantity can also be written as the CDF of the residual evaluated at the point V hat. So at the end of the day, what we need to do is only to construct a conservative estimate of the 1 minus alpha quantile of F tilde. So how can we do this? We do this by first constructing an envelope function for the CDFs. So let GT be this envelope function, and we require it to, for each T, GT is less or equal than the infimum of F2 to T. So it's an lower envelope. In fact, we can write down an explicit construction of this envelope function. So here, GT takes the form of the maximum of two expectations. Note that GT here is identifiable because it's all the quantity here are observable, but it's still a population quantity. So the next step is to construct a lower confidence bound for this GT, such that it is a lower bounds GT for probability at least 1 minus delta. So because we only need this to hold for fixed T, instead of for all the T simultaneously, this can be done by standard concentration inequalities. And finally, we construct the prediction interval and choose the cutoff to be the 1 minus of a quantile of this G hat T, the lower confidence bound. We show that if the superpopulation satisfies the marginal gamma selection condition, then it achieves exact Pac-Type guarantee when, again, the upper and lower bounds are exactly known. It achieves approximate coverage when they're estimated, and the estimation error depends on how well it estimates the upper and lower bounds. We also show in the paper that this procedure is tied for some classes of problems. And we also give an exact characterization of the range of the target distribution. And so I will leave these part out in my presentation. So having known how to construct predictive intervals for the counterfactuals, it is then easy to construct predictive intervals for the ITEs. Again, as we mentioned in the beginning, when there is only one outcome missing, we just need to construct predictive interval for the potential for the counterfactual and take the difference. When both outcomes are missing, we construct two predictive intervals with the Bonferroni correction because we need to take the union bound, and then merge these two predictive intervals in a conservative way. So the new predictive interval for the ITE is valid. So yeah, so I've finished the part of constructing predictive interval for the ITEs, and the next part would be making use of these intervals and make causal conclusions. Before we go into that, I am pause one more time to see if there are any questions.
Yeah, there is a question about the conservativeness or about the length of the conformal predictive interval. So it says that conformal confidence interval might be typically larger than confidence interval for CAT practice. So it might be too wide to guess statistical significance. Is there a way to translate this concept to Bayesian and form a Bayesian type conformal posterior?
Yeah, thanks for this question. So yeah, potentially the predictive interval of, well, it depends on a lot of things. It could be the case that the predictive interval is wide, but it is because we are dealing with a completely different problem. We are trying to give uncertainty qualification for some random variable. So the random variables themselves already have randomness in them. This is different from the confidence interval for ATE or CATE because those population quantities, they are not random. So these are two different type of questions. So it's hard to compare them. And both of them have use in their own area. And as for the Bayes question, yeah, I am not an expert on that, but I assume, well, for the conformal inference problem, it is completely model free, and also there's no parameters or models in our case. So I'm not sure how we are adding priors in this case, but it is, I assume it is probable we can do something in terms of understanding, we can take a Bayesian perspective and understanding covariance, the distributional shift in this case. But again, that is potentially an interesting topic, but I cannot answer too much at this moment. Thank you. Are there other questions?
There are no other questions. We can continue. Thank you.
All right, just
Thank you,
to remind you, so you have around 10 minutes left.
Okay, sure. Yeah, so yes, now we've known how to construct predictive intervals for the ITE, then we make use of them. So in observational studies, people make causal conclusions using sensitivity analysis. It gauges the robustness of causal conclusions against possible confounding. So what sensitivity analysis does is that we consider a sequence of confounding strength, and at each level we detect whether there is whether there is a treatment effect, and then we continue increasing this confounding strength and record the strength at which we cannot detect the confounding the treatment effect. And then roughly speaking, the idea is that either there is a treatment effect or the true confounding level is greater than the reported one. So we try to formalize this thinking in our framework and to make a rigorous statement about this. And in fact, we can do this by, we can equivalently write this as testing a sequence of hypotheses. So it goes like this. Suppose gamma star is the true unknown confounding level. So sensitivity analysis is actually equivalent to simultaneously testing a sequence of hypotheses indexed by gamma. So gamma is the index in the marginal gamma selection condition. So here the H0 gamma is under H0 gamma, either Y1 minus Y0, the ITE is in some set of interest C, or, and the gamma star, the true confounding level, is lesser than gamma. So here, rejecting this null means either the causal conclusion is non-null or the confounding strength is actually larger than gamma. So our testing procedure is simple. At each confounding level, gamma, we construct a predictive interval using our previous robust conformal inference procedure. And then if this predictive interval does not intersect with C, the set of interest, we say we reject the null, otherwise we don't reject the null. We can show that our testing procedure controls the probability of rejecting any null, and the probability of making a mistake is controlled by alpha. So what can we make out of this? So to understand what's happening, we define the gamma value, which is the smallest gamma, such that we cannot reject H0 gamma. Because our procedure, because our predictive interval C hat X gamma is nested, our rejection set is in the form of an interval. So the interpretation of this gamma value is that, roughly speaking, ITE is not in the set of interest unless the true confounding level is greater than this gamma value. So if we have any background knowledge that excludes the possibility of having such a large confounder, we can have confidence in that there is actually a significant ITE. So as a concrete example, if the set of interest is negative infinity to 0, we're testing for positive ITEs. So the guarantee translates to the probability of Y1 lesser or equal than Y0 and gamma value greater than the true confounding level is bounded by alpha. So here, because our null hypothesis involves the random variable Y1 and Y0, so it's a random hypothesis. In the case where we have a deterministic hypothesis under the null, the gamma hat, the gamma value is indeed a 1 minus alpha level lower confidence bound for this true confounding level. So these are our methodologies. And in the following, I am showing some numerical experiments with our methods. The first one is a simulation setting where we test the counterfactual prediction. The setting is adapted from the simulation setting in a paper by Jadlowski et al. In 2018. So the task is to do counterfactual prediction of Y1 for the superpopulation. So now we're doing it for the superpopulation. And here is how we generate the data. And then we generate data in a way such that the confounding level is exactly what we want it to be. And we consider a sequence of confounding level. So these details are not that important. The important thing is that the setting tries to be adversarial, meaning that we try to let the observed treatment effect actually comes from the confounder instead of the true treatment effect. And then we evaluate our method by running it again with a sequence of alpha, and we set delta to be 0.5. We test both the methods with both guarantees, and for marginally valid, so for both of these methods, we're running it with estimated propensity score, which means we're using estimated upper and lower bounds for the likelihood ratio. And then this plot represents the result for the marginally valid procedure. Here, the x-axis is the target coverage, and the y-axis is the actual one. And then the solid lines represent our method under different gamma values. And then they are all above the 45-degree line, meaning that they're all valid. And then they are pretty close to the 45-degree line, so they are pretty tight as well. And the dashed lines are the methods without adjusting for the covariate, the confounders, and they are below the 45-degree line. So there is indeed a need to adjust for the confounder. And this is the result for the high probability valid procedure. Here, what we're plotting is the quantile of the coverage. So they should also be above the 45-degree line. And here, we actually see they are almost exactly on the 45-degree line, meaning that they're both valid and very efficient. Finally, we apply our method on the real data set, the NSLM data set from the ACI's data challenge. So for those of you who do not know what NSLM is, it's the National Study of Growing Mindset, a learning mindset. So we consider the ITE on the treated, so we only need to construct predictive interval for Y0. We test two kinds of hypotheses. The first one finds the positive ITEs, and the second one finds negative ITEs. And here we choose alpha to be 0.1 and delta to be 0.05. So first, for the hypothesis that finds positive ITEs, these two plots are the proportion of rejections as a function of the confounding of the gamma value. The left-hand side is the result for the marginalized guarantee, and the right-hand side for the Pac-Type guarantee. And for both of these two cases, we can see at level gamma equals 1, about 20% of the test treated units are identified as positive. And as we increase the confounding level, there are still some samples. So the lines are still above 0. So there are some samples that have very large values of gamma hat, meaning potentially they have true ITE, significant ITE. And here we are plotting the gamma value as a function of the school achievement level. So the school achievement level is one of the covariates that we use in this data set. And this is the result for testing negative ITE. So we see less proportion of rejections, and at gamma equals 1, there are about 3.5% of the treated unit. Okay, so that concludes my talk. Our paper is online, so feel free to check out the details. And thanks everyone for the attention.
All right, thank you so much for the very nice presentation. We're now switching over to discussions. So Stefan Wager will present some slides, and after that, Zhimei, you will have the opportunity to respond. So Stefan, whenever you're ready.
All right, just gonna share my screen. All right. Well, yeah, thanks a lot for this very nice paper. Thanks for inviting me to discuss it. And thanks also, Zhimei, for the very nice talk. So this paper is about treatment effect estimation in the potential outcome setting. So it's by now a very standard model. We have potential outcomes yi0 and yi1 corresponding to the outcome the IT unit would have gotten with or without treatment. This lets us define the individual treatment effect, delta I. The difficulty is that for each unit, we never get to observe both treated and control potential outcomes. We only get to observe the outcome corresponding to the treatment we assign to the unit. And then there are a bunch of questions we can ask. In most of the causal inference literature, a starting point of the discussion is that these individual treatment effects, delta I, although they're interesting, they're unmeasurable, somehow unknowable. I need to treat you or not treat you. So somehow the difference between what would have happened to you specifically in treatment versus control is unknowable. So then we focus on estimating targets that are identified, like the average treatment effect or the conditional average treatment effect. So that's cool. But this paper it doesn't want to stop here, and it considers this much more ambitious task of actually trying to say something about the individual treatment effects. So the way I see it is this is kind of a two-part contribution. First from this earlier paper by Li Hualei and Emmanuel Candes that kind of sets out how to do conformal inference in this setting, and then the paper we heard about today that adds sensitivity to unmeasured confounders. But so first, just why is this such a difficult task? The ITEs are not identified, so all we can hope for is bounds. And just to kind of highlight why something simple just doesn't work, suppose, like was done in the talk, that we have a sample that's assigned to control. So the control potential outcome is observed. You'd want to know the ITE, so that's yi1 minus yi0. If you wanted to estimate it, really kind of the only reasonable thing to do is to try to predict yi1, so what would have happened to you in treatment, and then have you estimated ITE be y1 minus y0. But this, of course, is not going to be consistent because there's some irreducible noise, unknowable variation in yi1 that you can't recover from estimation. So what can we do instead? And here, the paper we heard about today really is a very nice combination of a lot of ideas in the literature to make this possible. So the first ingredient that goes in is to use conformal inference to reason about the discrepancy between the actual treated potential outcomes and your best estimate of them. Like in the paper, earlier paper by Li Huan and Emmanuel, there's a use of propensity weighting to account for distributional shift between the distribution of y1 for treated versus control samples. And then, and this is the main new contribution of this paper, there's a use of a marginal sensitivity model to adjust for potential unmeasured confounders. And the authors provide strong formal and empirical evidence that this approach then works. So again, since this is kind of the main novelty of this paper, this step 3, I wanted to just kind of say a few words of at least how I interpreted the main idea here. So in order to carry out conformal inference in this setting, what you need is the following. Essentially, if we write P0 as the joint distribution of X and the treated potential outcome for control samples, P1 is the same thing for treated samples, then you need access to this density ratio function, dp0 of dp1, that lets you essentially look at XY pairs on the treated sample, because on the treated sample, Y is equal to Y1, and then reason about how to transport facts you learn about this distribution over to the control distribution, because you want to kind of impute Y1 for a control, a unit observed in control. If there were no unmeasured confounders, then a famous result in causal inference is that this transport function takes on a simple form and only depends on the propensity score, the probability of being treated conditional on X. Given this observation, you can proceed, and that's what Lei and Candice do. But here, authors are not willing to assume no unmeasured confounders. They relax this, and instead what they assume is that this transport function W is pretty close to this thing rho you would have gotten under no unmeasured confounders, but not quite. There's this sensitivity parameter gamma such that this transport function is within a factor gamma of rho. So now this transport function isn't identified anymore. It's in a set. And the challenge is to provide conformal inference that's robust to kind of anything that could happen within this set. So yeah, you need to kind of reason about what's the least favorable distribution in this set. How are you going to do this? And now there are kind of a lot of things going on. One key idea, when you look at this, you might think of linear programming because you see linear constraints. When you really stare at it, it turns out that then, of course, like the authors explained, this is a fractional linear program because the weights have to have expectation 1. So it's a change of measure. This constraint set leads you to a fractional linear programming problem. It turns out it's tractable. It turns out that in the setting considered here, it actually has a very nice interpretable solution. Essentially, being conservative means find those samples where you have large residuals that make your intervals, conformal inference intervals wide, upweight those, find the samples that make your intervals shorter, downweight those, and that's going to make you conservative. And this is well aligned with results with sensitivity analysis for average treatment effect type problems. But of course, the conformal inference is a very, very different setting in terms of the details, and it all works out very nicely. So that's the main idea. I wanted to kind of close with 2 questions and a comment. A first question is, I mentioned, right, that if you wanted to get point estimates for the ITE, the only reasonable thing to try would have been the following: it's inconsistent. So stop here, let's do conformal inference. But actually this point estimator construction does play a somewhat bigger role than this in the method proposed by the authors, because essentially under the hood, this regression is being run. So you learn to predict Y from X in treatment on the treated units, and then you look at residuals of this regression, and this is what gives you the nonconformity score that lets you proceed. So the question here is that, okay, fitting this regression, predicting Y from X untreated to kind of get a starting point for Y1. This makes sense under no unmeasured confounders, because in this case, you have this relationship. But under unmeasured confounding, actually, it might be that your best point estimate of YI1 is not the same as your best prediction of Y given X and that you're treated. So this is really a genuine question. Is there any way to improve power for conformal inference by building your intervals around something else than this mu hat 1, something that accounts for kind of possible pessimistic distributional shift on unmeasured confounders in this setting? Or is the way the recipe goes that there's really nothing to do here? So that's the first question. A second question is that yeah, this obviously under the marginal sensitivity model, this constraint is really kind of the key thing to focus on. A lot of the power derives from here, but there are other consequences of the marginal sensitivity model that arise. One that I mentioned briefly just a couple slides ago is that this weight needs to be a change of measure thing, so it needs to have expectation 1. But actually more is true, right? And this is briefly commented on the paper, though not in the talk. And that's that we know the x marginals of both P0 and P1. So this means that we kind of, if we condition on x, we know what the expectation of the weight function is. And the question is, how can we best exploit this fact? In the paper, there's a brief comment on how you could do this kind of by looking at conditional distribution of the weight function, but this requires essentially solving quantile regression. So it's pretty hard. One other approach I just wanted to ask about is that a kind of weaker way to use this implication is just that for any test function psi that depends only on x, kind of a consequence of this is that the W-weighted expectation of psi of x on the treated units has to match the expectation of psi on the controls. So this would allow you to, using this kind of constraint, building it into the conformal inference pipeline, would allow you to kind of use this fact without having to really do conditional on x stuff. You could just, in practice, pick up a handful of dictionary functions psi, balance those out, and then be done with it. So this kind of approach has worked out well for average treatment effect estimation. There are a bunch of references. I just put a few here. But now, full disclosure, of a recently graduated student, Synchrony and Hito Embens, we have a kind of in progress working paper where we've been exploring this kind of idea in terms of a different sensitivity type problem. So I guess this is more just an invitation to I guess talk more. I'd be very curious if this is a way to improve power here. Anyways, the last thing I just wanted to comment on, this was something I was struck by in the talk. I often get the impression that sensitivity analysis, it's like statistically very expensive. You start from short intervals and you get something very, very wide. This is a graph from the working paper I was just describing. But in this talk, you seem to be getting very good power out of conformal procedures. So what's going on? The answer, of course, is obvious. Average treatment effects, we use to confidence intervals of length 1 over root n. We want to be robust to failures of unconfoundedness. We get an order 1 fattening to the intervals. That's expensive. For ITEs, the best you could hope for a conformal inference is already a O of 1 interval. Sensitivity analysis adds an O of 1 fattening, but maybe that's not so bad. Certainly it doesn't stand out in the same way. So I thought this was cool and really highlights the promise of sensitivity analysis when paired with conformal inference. Anyways, that's all I had for today. And yeah, thanks again, Zhimei, for the very nice talk, and to all the authors for the very nice paper.
Yeah, thanks for the very nice discussion. Zhimei, if you want to respond.
Yeah, sure. Thanks a lot for the nice interpretation and the wonderful questions. In fact, all those 2 questions are something that we considered when we were writing that paper. But we somehow, after some thoughts, didn't end up talking about those in the paper, but it's definitely still in our heart. And for the first question about the predictive model, in our paper and in our simulations, we are just using the method, the predictive model that does not take into account the confounder. We're actually using the GRF package. So we thought about that. We were thinking of using some robust model that take into account the potential unmeasured confounder influence to build up this model, but we have not experimented with it. This is potentially a next step. And for the second question, indeed, that's something we thought a lot about when we were writing the paper. So the bounds on WXY jointly is, of course, a necessary condition instead of a very sharp characterization of the distributional shift. In fact, in our paper, in the Pac-Type case, we do have a procedural that, well, not exactly procedural, a section that characterized the sharp way to conduct predictive inference for exactly the counterfactual prediction problem. But that requires, as you said, the estimation of conditional quantile on X. And we do not want to do that because we want to remain, well, the main advantage of all this conformal inference framework is that it's model free. We do not want to sacrifice this to estimate this hard object. But indeed, it is interesting to understand how we can do better to achieve better sharpness in this case. And yeah, as you suggest, the covariate balancing approach is definitely a very tempting one, and we would like to think about that if we can incorporate that technique in our framework. And thanks again for all your wonderful comments and questions.
Thanks.
If I may just add one thing, just that there was a question in the chat about linking this with Bayesian analysis. And so in the case where perhaps you have a good Bayes model, you could use this to actually build conformity scores. And of course, this will all be conformalized, and you could get a boost in power if you were to start from a good Bayes model. So just to link a bit Stefan's question with earlier questions in the Q&A that I could see, I think Stefan is exactly right in thinking about conformity scores that would bring enhanced power, and is making very good suggestions. There was also a suggestion in the Q&A about using Bayes model. I think this is all good stuff that we could use to deliver sort of narrower intervals.
All right, great. So if there are no further comments, I'll quickly wrap up. So yeah, first of all, thank you so much, Zhimei, for a very nice talk, and also Stefan for a very interesting discussion. Also, thank you to Ying and Emmanuel for helping out in Q&A today. Next week, we're going to have Luke Keel from the University of Pennsylvania, who will talk about so many choices, the comparative performance of statistical adjustment methods. Yeah, thank you all for coming. Hope you have a great week, and see you next time.